Hello and welcome to Lecture 3. In this lecture, we're going to be talking about association. So association is a type of relationship that can exist between two variables. And let's just use a silly example to get us going. So let's say you've noticed that people with big feet are tall, and it would appear that people with small feet are shorter. But you have noticed every now and again someone with big feet who's short, and you're like, oh, well, that's a little odd. I mean, how often does that happen? Well, if you want to convince your friend of this, you could, go out and recruit a whole bunch of people and line them up and have a look at by height, and then have a look at their feet and go, oh, is this relationship true or not? But this is a little tedious, and you may want something a little more scientific. And so this is where Pearson comes in. So he's a mathematician, statistician from the late 1800s, early 1900s, who describes what he calls the linear correlation coefficient. And it is a statistical means of showing this association that you are hypothesizing. Now, he's also very well known for the chi-square, for the principal components analysis, and he's also known for biometrics. So this idea of a mathematical reasoning for evolution and inheritance. As always, let's use an example. So a matched pairs design was used in 2 studies to compare the decrease in blood pressure over 6 months on drugs A and B. Now, an association between blood pressure changes in members of each pair was only apparent in study 2. Now, the first thing you should do when you receive a data set is plot it or visualize the data in some way. And this is probably the best advice that Paul and I are going to give you in this course. I'm kidding, but it's really important for you to always check your data and visualize it before you get going on the analysis. Now, in this case, what we're doing is we're plotting the change in blood pressure on drug A on the y-axis and the change in blood pressure on drug B on the x-axis. And what this does is it gives us a 2-dimensional representation of our data. And what we're interested in is the relationship, the association, the correlation of the drop in blood pressure between our 40 matched pairs. Now you can see in study 1 that the data is spread out quite evenly around the entire space, your 2-dimensional space. And it doesn't, I'm going to say inevitably because, I'm so used to looking at data that there's no relationship. But you might say, well, yeah, there's a relationship. It's nice and circular. So don't forget, what we're trying to do is look at, some form of organized change between the 2 axes. And in this case, it doesn't seem like there is any. Whereas when you look at study 2, there is this form of organized change between the 2 axes. And in this one, it would appear that as you increase the drop in blood pressure in drug B, the drop in blood pressure on drug A also increases, and you get this kind of linear formation that's apparent in your data. All right, so we're interested in describing this relationship between the 2 variables, and we're looking for a form of organized change or direction of the data. And what we've done to make it easier is we are drawing horizontal and vertical lines through the plot means. So just through the mean in change in blood pressure on drug B and the mean in change in blood pressure on drug A. So these are what this cross represents. Okay? And then what this allows us to do is it split the plot into 4 quadrants. And what we can look, and inevitably you can say, okay, well, what can we do now? Well, what you can do now is you can count the number of points that exist in each quadrant. So interestingly, in this one, you'd almost say, well, it's almost actually quite even. There's, even number of points in each quadrant. Whereas in this one, interestingly, there's actually no points in this quadrant, and there's quite a few in the top right quadrant and quite a few in the bottom left quadrant. And there's a sprinkling here, in the bottom right. Does that mean something? So inevitably, you're thinking, yeah, I think, there must be something to these numbers. So how might you quantify this association, right? And the number of points for each of the four quadrants are listed here for you. And you can, definitely see that, these in drug A, the numbers for each quadrant are quite close. Whereas in drug B, as we already described, the top right and bottom left are definitely much higher in terms of number of points than the top left and bottom right. And so this must mean something. So our first stab at coming up with a measure of association might be something as simple as the proportion of points in the top right and bottom left quadrants, because that's where we see most of the activity going on, right? And we're like, this must mean something. So let's call this R1 as our first measure. And in study 1, R1 would have 19 out of 40, so there's a total of 40 data points on the plot, and 19 of them reside in those two quadrants of interest. And the proportion is 0.475. In study 2, R1 is going to be 33 out of 40, which is a proportion of 0.825. So is that helpful? So a weakness of this definition is that it can only be positive. And this is because we have not taken into account the number of points in the top left and bottom right quadrants. So in terms of the study 2, this is probably, you're like, well, that's okay, there's not very many points. But for study 1, that wouldn't be fair. And so a large proportion of points in these quadrants would indicate a negative association, correct? Because it would be the other direction, going from left to right and down. Therefore, we will subtract the number of points in the top left and bottom right quadrants from the total in the top right and bottom left quadrants and divide this difference by the sample size. Okay, so this is our next change to our statistic. All right, this is what we end up with. So for our second attempt at a statistic, we have for study 1, we're going to take the number of points in the bottom left and top right quadrant, subtract away the number of data points in the top left and bottom right quadrant, and divide by the total, and we get a negative 0.05. In study 2, we take the total in the bottom left, top right, which is 33, and we subtract away all of the points in the top left, bottom right quadrants, which is only 7, divided by the total, and we get 0.65. Now it's interesting to note, if all points were in the left, bottom, and right top quadrants, then our the statistic that we're creating here, R2, would be equal to 1. And if all points were in the top left and right bottom, then R2 would be equal to negative 1. So this is starting to look, I'm sure, very familiar to you. And we're going to now just polish it off in the next. Okay, let us create a formula that captures what was done in the calculations of this measure. So we're going to replace x by a new variable sx, which is the sine of x. And that is equal to +1 if x is to the right of the vertical axis and -1 if it is to the left of the vertical axis. Makes sense, right? Similarly, y is replaced by a new variable, sy, the sine of y, that is equal to +1 for values above the horizontal axis and by -1 for values below the horizontal axis. So our general formula is now going to look like what is here listed here. And so this just means the sum of, and this is the sine of x multiplied by the sine of y divided by the total. In our case, it's 40. So we still have a bit of a problem. And that is that one defect of this measure is that it gives a value of +1 or -1 to Sx and Sy, depending on which quadrant they are in, but it neglects any information on the size of X and Y, which in our case is the change in blood pressure in groups A and B. That would be nice to be able to incorporate that change. And so a possible improvement would be to replace Sx and Sy by the difference from their means. Now, we've seen this before when we were calculating variance. All right, so hang on, we're almost there. So here, our third suggestion, we're going to call it R3, is for the measure of association between X and Y is going to be the sum of the difference of X from its mean times the difference of Y from its mean divided by the total. Now, unfortunately, there's still a bit of a problem. And, a defect in this measure is that its value would increase if we changed our units of measurement, say from inches to centimeters. And this would be a problem for our measure of association. So, as we've seen before already, we must standardize these two deviations from their sample means. Each difference then is simply going to be divided by their standard deviations. Now in this case, you'll note that the sum of squared deviations are going to be divided by n instead of n minus 1. If you remember when we were calculating the variance, we divided by n minus 1, and we explained why we were doing that for an unbiased measure. Okay, here's the math for R4, our fourth attempt at a measure of association. Now, if you have a look at the top, this is the sum of the difference of X from its mean over its standard deviation multiplied by the difference of Y from its mean over its standard deviation, all of it divided by n. If we rearrange this equation, we end up with this lovely equation at the bottom, which, as you can guess it, I'm sure, this is the Pearson coefficient of correlation. And voila, we have successfully duplicated what Pearson put together many, many, many years ago.